Hey folks, Ms. Gosling here. In this video, you're going to learn about angled forces. By the end of the video, you'll be able to determine the value of missing forces in equilibrium problems involving forces applied at an angle. So let's go ahead and get started. So with angled force problems, as with linear force problems, we do want to start by drawing a free body diagram and determining the magnitude of known forces, as well as figuring out what our unknown forces are. So we want to start with a picture and with our known. With our knowns and our unknowns, or our givens and our unknowns, excuse me, just like with the guess method with earlier questions. We can use this, so once we've done that, we want to go ahead and split all of our forces into x and y components, set our forces in the x direction equal to 0 and our forces in the y direction equal to 0, and solve for any missing forces. So let's go ahead and go through an example problems so you can see how this is all, a couple of example problems so you can see how this is all done. So example 1. A 70.0 kilogram box is pulled at a constant velocity by a 400.0 Newton force at an angle of 30 degrees to the horizontal. Find the magnitude and direction of all other forces acting on the box. So let's go ahead and get started. So, first of all, our box is being pulled at a constant velocity. That means its acceleration is 0, so it is in an equilibrium, i.e., the sum of all the forces acting on the object is equal to 0. Now, we want to go ahead and draw a free body diagram for the box. Now, a lot of folks like to try to draw their free body diagram on the picture, so we're going to do that first. Then what I'm going to do is I'm going to move the free body diagram off the picture into empty space so that it's a little easier to see everything that's going on. So, let's start with a dot to represent the center of mass of the box. We know that we have that 400 Newton force being applied at a 30-degree angle. We also know that the box has mass and is on Earth, so we have a gravitational force pointing down. Balancing out that gravitational force, we know that there must be a normal force, and I'm going to go ahead and, since my normal force is unknown, I'm going to go ahead and draw my normal force in blue. Finally, we know that there must be something balancing out the horizontal motion of the forward horizontal motion of that applied force, and that force must be the force of friction, since it is parallel to the surface the box is being pulled across, and is resisting that change in motion. So these are our 4 forces acting on our box. And let me go ahead and draw that 30-degree angle in as well. From here, I can go ahead and I can pick up my free body diagram and move it so that it's easier to see what all the forces are on the box without being distracted by the picture of the box and the dude. Next, we want to go ahead and break our angled forces up into their x and y components. So to do that, let's take a look at our 400 Newton force. And I'm going to go ahead and draw up above our problem here. So our 400 Newton force is at a 30-degree angle, which means it has both an x component and a y component, which I'm going to call fx and fy. That y component of my force is opposite the angle, so that means that my force in the y direction is equal to 400 times the sine of 30 degrees, and my force in the x direction is adjacent to my angle. It's touching the angle that I'm given, which means that it's equal to 400 times the cosine of 30 degrees. Plugging that into my calculator, I got that my force in the y direction is 200 newtons, and my force in the x direction is 346 newtons. Now that I've broken my angled force up into its x and y components, I am ready to fill out a t-chart to help me sum up my forces in the x direction and the y direction. So I have 2 forces acting in the x direction. There is first the x component of my angled force. So that is going to be So if the x component of my angled force, which I'm going to call Fx, And I can see from my free body diagram that my angled force is pulling in the negative x direction and the positive y direction, because it's going up, which is positive in the y direction, and to the left, which is negative in the x direction. So in the x direction, I have negative Fx. And then I also have my force of friction, which is to the right, so it's going to be in the positive direction. In the y direction, I have the y component of my applied force, Fy, which is positive since it's up. I have my gravitational force, which is negative since it's pointing down. And I have my normal force, which is positive because, again, it's pointing up. Excuse me, it should be Fn. Let's fix that. And I know that in both x and y, the sum of my forces is equal to 0. Now that I have laid out the forces in the x and y direction, it's a little easier for me to write my equations for x and for y to allow me to solve for any of my missing forces. So in the x direction, I have the negative Fx, or negative 346 newtons, plus my unknown, my mystery frictional force. And when I add those together, what I get is that my net force is equal to 0. That means that my frictional force must be positive 346 newtons to balance out the x component of my applied force. Similarly, in the y direction, I have the y component of my applied force, or positive 200 newtons. I have the force of gravity, which is going to be 9.8 times my mass, so 9.8 times 70. And I have my y component, and I have my normal force, so plus Fn. And again, since our object is not accelerating up or down, that means that our net force is going to equal 0. So when I add those together, I should get 0. Simplifying this, I get that 200 plus 686 plus my normal force is equal to 0. Or excuse me, sorry, 200 minus 686, got to remember our directions, plus our normal force is equal to 0. Thus, our normal force is equal to 486 newtons to balance out both our y component of our applied force and our gravitational force. Now let's look at a slightly more difficult question. A 1 Newton donut is being held up by 2 strings, each at a 45-degree angle to the ceiling. What is the tension force in each string? So let's go ahead and take a look at this question. So again, starting with our free body diagram, we know that there is a gravitational force of 1 Newton pulling down on the donut. We know that there is also a tension, which I'm going to call Ft1, from our first string. And that is going to be at a 45-degree angle to the ceiling. So if I were to redraw that picture here, I'm at a 45-degree angle to the horizontal. Similarly, I have Ft2, which is again at a 45-degree angle. Taking my picture of my forces, my free body diagram, I can move that up to the top to simplify things. I also know that my tension forces should be the same. So I'm going to go ahead and just call them Ft and Ft. The reason I know this is that they're the only forces acting in the horizontal direction. So that means that the force of my first string in the horizontal direction has to be equal to the force of my second string in the horizontal direction. Since they're at the same angle, that means that the forces in both strings must be the same. So now that I have done this picture, let me go ahead and simplify and separate my tension forces into their x and y components. So for the first tension force, actually for both tension forces, what I will find is that Ft in the y direction is equal to Ft times the sine of 45, since my y component of my tension force is opposite my angle, and Ftx is going to equal Ft times the cosine of 45, because my x component of my force is next to the angle that's given. This is going to allow me to figure out to create my t-chart in x and in y to list out my forces. So in the x direction, I have positive ft times the cosine of 45 from my first string, and I have negative ft times the cosine of 45 degrees from my second string, since my two strings are pulling, since one string is pulling to the left and the other is going up and to the right. Summed together, that is going to give me a total force of 0. Similarly, in the y direction, what I will get is that I have the force of tension times the sine of 45 from my first string in the positive direction. I have the same for my second string in the positive direction. And I have the force of gravity going in the negative y direction. And again, those forces are going to sum to 0. Now, I could use the x direction to prove that the tension in each string has to be equal to one another. I'm going to let y'all do that if you're interested in exploring, because it is in the y direction that I will actually find what my tension force is. So in the y direction, I have that ft times the sine of 45 plus ft times the sine of 45 minus 1 is equal to 0. What that gives me is that 2 times ft times the sine of 45 minus 1 is equal to 0. Thus, 2 times ft sine 45 is equal to 1. And dividing both sides by 2 times the sine of 45, I get that ft is equal to 1 over 2 sine 45, or 0.71 newtons. And there we go. That is the tension force in each of my two strings. So that brings us to takeaways. First of all, an object that is moving at a constant rate, and when I say constant rate, I mean constant velocity, is in equilibrium and has a net force of 0 newtons acting on it in both the x and y directions. Secondly, it is important to split angled forces up into their x and y components to find the value of missing forces. With that, you now know how to solve equilibrium problems with angled forces, so give it a try on your own. Best of luck and happy solving.